So this first one was a study that was brought to me by TGS, and they wanted to analyze to see if paradise could be a predictor of production in the Meramec Formation in central Oklahoma, which is an unconventional resource. Where the wells were, this is 196 square miles of data, and TGS really shot some beautiful data in here. But I have wells color-coded by their production. At the north, I have the production in green, and those wells are generally in the 25,000 barrel or less production. The ones in pink are anywhere from 40,000 up to 90,000, and then down here at the bottom, I don't have a pointer on this. Down here at the bottom, there's one well in red. That's the 𝗟𝗲𝗿𝗶𝗴, and it produced 240,000 barrels. So it's a standout compared to all the other wells in this study. What makes it a standout? I'm here to try to find out the difference. Here's a time structure map on the Meramec, and you can see that you're going into the basin as you go to the southwest. As you would figure, this is the Anadarko Basin here. And the contour interval is 10 milliseconds, which is approximately 60 feet. Here's an example of the section, and you can see that the section thins as you go to the north because as you're going deeper into the basin, everything thickens. The reservoir, the source rock in here is the Woodford, and the Meramec is that pink line kind of going through the middle. Let me see. So this is the top of the Meramec right in here, and this is the top of the Woodford right here. And so most of the wells in here, the straight holes, over the years had just been, they hit the top of the Meramec, they just perforate the whole interval and blow and go on down the road. But like I said, there was such a disparity in the production, I kind of wanted to know why this one well at the very left end of the cross section did so well. 240,000 barrels compared to an average of about 40,000 barrels. So we go through a process first as part of the workflow called principal component analysis. And what principal component analysis allows us to do is take all the attributes that we've created, lump them into one pile, give them kind of a zone. Okay, I want to look at all these attributes between the top of the Meramec to the bottom of the Woodford, and it will go through and sort out those attributes which have the most variance in that zone. So what this allows us to do is find kind of the best group of attributes and get rid of the redundancy, because you don't want to do these SOM analysis with 19 or 20 different attributes. In this particular case, which is not the Meramec case, I'm showing that in the first principal component, the highest eigenvalue sorted out the top 4 attributes. So those will be the top 4 attributes I'd want to look in my recipe of attributes I'm going to use for my neural analysis. And those 4 attributes themselves account for more than 93% of the data found in all 12 attributes in this example. So these are the top dogs. Then the second highest eigenvalue is in the second principal component. And then those next 3 attributes account for more than 81% of the remaining information. So right here in the first 2 eigenvectors, I've picked out 7 attributes out of 12 that probably will give me more information than trying to use all 12 themselves. In the case of the Meramec, I went through and I had I did a window, like I said, from the top of the Meramec to the base of the Woodford, and I had 19 different attributes, or 16 attributes. And so the first eigenvalue was sweetness, envelope, frequency, thin bed, and smooth frequency. So this is telling me that not only am I seeing hydrocarbon effects, but I'm also seeing very thin reservoir possibilities in here, because the frequency is going to say you're looking at thin beds. And I built a recipe, and I have the recipe here on the bottom of the slide, because I added a few things more that I knew in the area would help. Like Robin said, I've done this enough years. I think I've been working on Paradise probably since 2013 or 2012. So a lot of years in this all over the world for people. There's very specific sets of perforations in this particular well. And while most of the wells just blasted all of the Meramec, the 𝗟𝗵𝗂𝗏 or Gulf oil blasted most of it. Then it hit very specific zones, especially the bottom set of perforations, which happen to be kind of brown and yellow in this color scheme. And that's neuron number 71 and neuron number 72. And of course, they sit right on top of the source rock, which is interesting. But it's also interesting that they didn't just blast the whole thing and go on down the road. When I looked at those two particular clusters, I saw that they tied to the best resistivity of in the rocks. So usually when you're working in unconventional reservoirs, you like to see a higher resistivity because it means more brittleness. You probably have a better fracking capability. Now, they did frack these straight holes back when, so I'm sure that this set of neurons right here probably was the best productive part of all the production that well did in the perforations because it had the best resistivities. So here's a display. We can turn on or turn off any one of the clusters in the map, just like the example of the 𝗍𝗶𝗶 with all the statistics for the different countries. And I can isolate just those two sets of neurons that I'm interested in and look at their distribution across 196 square miles for data. And I noticed that the efficacy was the only one that had both the yellow and the brown. Most of the other good wells, decent wells, and the 50,000 to 90,000 group were only in the brown. And all the poor wells towards the north just didn't hit anything at all. So what I wanted to do in looking at production is we know the bin spacing of the 3D, we know the sample rate. We can turn these pixels into miniature volumes. All we need to know is we need to know the net to gross ratio, we need to know porosity, we need to know salt water saturation, and we need to know an interval velocity. So I'm going to take and create the geobodies that Robin was showing you that he was doing in his modeling. And I'm going to calculate reserves from those geobodies. And so looking at the efficacy, I've highlighted the geobody that represents the perforations, the lower perforations in that well. And if you look at the hydrocarbon pore volume from all the samples, it shows 118,695,700 cubic feet from all the samples in that geobody. Now we've improved the software. I don't have to go through the exercise of creating acre feet anymore, but I'm showing the math for creating acre feet because usually in the reservoir engineering, you want to know how many acre feet, how thick, and what the recovery factor is. So what I did is I calculated the acre feet. I got a good average from a buddy of mine who worked at Marathon for the Merrimack in that area and used that as a recovery factor to calculate that geobody at that well should have produced 613,125 BOE. Now, I put everything in BOE to kind of make apples and apples in here. And the actual that the well had produced at that point was 611,685 for the well. So I was only about 2% off in calculating what the well should have produced versus what it did produce. So when I showed this to TGS, they said, Sacrey, you got lucky. Let's go try it again. So I went out there were 3 wells that produced from the brown neuron, not the yellow, because no one hit the yellow but the efficacy. And I went up to look at the production. Actually, there's 4. Look at the production for those 4 wells. Turns out that the one well, the Bernard number 2, did not produce from the Merrimack, but produced from a shallower zone in the Osage or the Big Lime. So I used the combination of the 3 wells that did produce from the brown neuron and then found one other well to add to that. But you can see that the Bernard, which produced almost 50,000 barrels, happened to produce from the same 2 clusters. They just weren't in the same stratigraphic zone, which tells me anywhere I found those 2 clusters, number 71 and 72, should be productive. Because here's 2 completely different stratigraphic zones where those 2 clusters were productive. And there was one other well up there at the top that had produced from it. It wasn't a very good well, but I took the combination of the 4 wells, that one geobody that those 4 wells hit, and I calculated the production from those 4 wells and compared it to the geobody. And if you look, So the total pore volume was 475,751 plus the 58,000 from the 𝗥𝗲𝗄 well. That gave me 481,681 BOE, and the actual was 475,751. So here I was a 2% error using 4 wells that hit that one geobody out of what they produced. So this is a very, very accurate way of calculating reserves.